All right, you may be asking, okay, we got this big table full of reduction potentials. Where do those numbers come from? What's our frame of reference for those? Why is something a negative 0.2 volts or a plus 0.4 volts? Well, I'm glad you asked. And the reason is all of those table values have been collected based on a reference half cell. And that half cell is a standard hydrogen electrode. We have to have some frame of reference for a 0 volts. What's our starting point? Where is 0 on our number line? Okay, so half of them on that table were positive, half were negative, so there has to be something in the middle there, right? So the standard hydrogen electrode, SHE for standard hydrogen electrode, is a basis of reference for all cells. So it's our energy, our E0 reference point for cells. And there's a figure in your book on page 912. I'll sketch one up here real quick so we can kind of see what it looks like. But a standard hydrogen electrode, if we think about what one of our beakers would have looked like in our first diagram at the start of the chapter, this one looks a little different. It starts out looking the same. It's a beaker with a solution in it. And that solution has 1 molar H plus ions. So a standard condition for hydrogen ions, right? 1 molar concentration of all ions. So it's 1 molar H plus, but this particular cell has a large tube, or relatively large tube, inserted into it. And inside that tube is a platinum wire, just our conductor, right? We've seen those before. And it's also got a piece of tubing going in where hydrogen gas is bubbled. So as the hydrogen gas comes out, it saturates the solution inside the big tube with hydrogen gas. That's our 1 atmosphere of hydrogen gas. Remember, at standard conditions, it had to be 1 molar concentrations of every ion and 1 atmosphere of partial pressure for every gas. So a standard hydrogen electrode involves reduction of hydrogen. So 2 H pluses plus 2 electrons makes H2 as a gas. That's the reduction of hydrogen, going from 1 plus to 0. Has to happen twice because you have to make an H2 molecule. Now this setup has E0 defined as 0 volts. That's literally our frame of reference. The standard hydrogen electrode is 0 volts, and all of our measurements are taken relative to that. If you get into some other chemistry classes later on, if you decide to take analytical or instrumentation, we get to some of those processes that are based on other reference potentials, and there has to be a correction factor used for those. But for us, we're looking at the standard hydrogen electrode as our frame of reference. Now, you're not going to see these in anybody's lab. These are kind of theoretical electrodes anymore because it's dangerous. It's expensive to buy all the hydrogen, you have to keep bubbling through there. But hydrogen's flammable. So this is a relatively dangerous electrode to have around, just bubbling all the time, just to have a reference electrode just for fun. That's one of the reasons we use some of those other reference electrodes I mentioned for our other classes. But this would be one of the half cells that gets hooked up either to a cathode or an anode, depends on which side you want it to be on, to make things flow. And it's how we measure the reduction potentials of all the metal ions. We hook up a standard hydrogen electrode on one side and the metal ions on the other, and we measure their ability to be reduced relative to hydrogen. But this is defined as 0 volts in terms of electrochemical potentials, the standard hydrogen electrode. And if you notice in the table in your book, the standard hydrogen electrode is in there. It's got two H pluses plus two electrons makes H2 as a gas, happening at 0 volts. So that's something we have to keep in mind. All of our potentials are relative to something else. Okay, just like 110 volt power line in your house is relative to what we call ground, and we define the ground as 0 volts. All of those values in the table are relative to hydrogen. So things that have a more positive reduction potential than hydrogen like to be reduced more than hydrogen does. Things that have a more negative reduction potential like to be reduced less than hydrogen does because of that spontaneity flip. Positive E cells or E zeros are spontaneous, negatives are not spontaneous. Okay? So we've been through a bunch of these examples in terms of calculating E zeros and things like that. If you can do one or two of them, you should be able to apply them to all of them if you follow the tips I gave you. And we've used this term spontaneous versus non-spontaneous based on the sign of E0. E0 is positive, it's spontaneous. That means there has to be a relationship to delta G, right? And to K. They all have to be related. Okay? That's where we're headed next. We're going to look at how E0 plays with delta G, K, and even, because of that, enthalpy and entropy, right? Because delta G was delta H minus T delta S, and if delta G is related to E0, then E0 also has to be related to those. So it's all one big family of conversions that could be done if you really wanted to, but G, H and S, and K are all related to each other. And that's where we're headed next.